Hello, and welcome to Water Quality. In this video, I'm going to show you how to solve the pH of a weak acid solution. So in this example, we'll use acetic acid, and we're adding 10 to the minus 3 moles to a liter of deionized water, and we want to find the pH. The first step that I'm going to take is to write out all of the relevant reactions. And that's the step that I usually take in these kinds of problems, and it allows us to identify the important species. So the first reaction I'm going to write out is the acetic acid reaction for a weak acid, and that is acetic acid donates a proton and forms acetate. And I'm using a shorthand for acetic acid here, which is HAC, because the chemical equation for acetic acid is a bit long. So HAC is our acetic acid. And the whole point of a weak acid is that it doesn't completely dissociate. So its reaction has, or is reversible. It can go either way. So in our solution, we're going to have both acetic acid and acetate, which means that the acetic acid doesn't completely dissociate. And this reaction has an equilibrium constant that's described as a K, and we use a subscript A to denote that it's an acid. And the value for acetic acid is 10 to the minus 4.7, meaning that acetic acid has a pKa value of 4.7. The second reaction that I'm going to write out is the reaction for water. And water is also a weak acid, and it dissociates into hydrogen ion and hydroxide. And the K value for this, I'll put a subscript W, is 10 to the minus 14. The next step after writing out the reactions is to write the mass balance equation. And because acetic acid does not completely dissociate, it's going to have both acetic acid and acetate in the final solution, and we want to keep track of that because the sum of those two things is going to be conserved. So we call that a CTA, which is basically all the places that acetate can be in the solution. So we have acetic acid and acetate, and the sum of those things is going to be what I added initially to the solution, which is 10 to the minus 3 moles per liter. Next step is to write out the charge balance. And the charge balance, I always put the positively charged ions on the left side, the cations. And in this case, I can see that the only positive ion I have is hydrogen ion. So I'll put that there. And then on the negative side, I have hydroxide and acetate. And that's it. The next step is to make replacements with the ions using the equilibrium constants and also the alpha equations. And our variable here is going to be hydrogen ion. So I'll leave that here. And then I'll use the equilibrium equation for hydroxide up above. And I'm just going to write it as Kw over H plus for right now. And that's because this Kw is the hydrogen ion concentration times hydroxide. And then I'm going to make a substitution here for the acetate. And I'm going to use the monoprotic alpha because acetic acid is a monoprotic acid. And this is going to be alpha 1 times CTA. And yes, we can write it out. Monoprotic acid. So we're going to use the monoprotic alpha. And I'll write that out in the next step. So I have hydrogen ion, Kw over H plus. And now my alpha 1 is Ka over Ka plus hydrogen ion. And don't forget the CTA value. The next step, I'll make substitutions. So hydrogen ion, 10 to the minus 14 for the Kw. H plus is right here. The Ka value is 10 to the minus 4.7, 10 to the minus 4.7 plus hydrogen ion, and this is times 10 to the minus 3. So now I have an equation where hydrogen ion is the only variable, and I can solve it. An easy way to solve this equation is to put the equation into your solver on your calculator. Alternatively, you could write a MATLAB code or put it into an Excel spreadsheet. So I used my calculator to solve this, and I got an answer of 0.000132 moles per liter, or 10 to the minus 3.88, which gives me a pH value, which is the negative log of H plus. So the pH is 3.88, and that is our pH of a weak acid solution where we have 10 to the minus 3 moles per liter of acetic acid.